this will be kind of our agenda here. I'll give a quick overview of this, and then we'll turn it over to Lance, and we should have time for Q&A at the end. And then the CEU credits, we can go ahead and offer those. We'll put up the QR code at the end so that they can, anybody that needs those credits can scan that QR code on your app for agronomy credits. And then the recording will be available later throughout the month, you know, the next 4 weeks or so, to be able to access that information. So always want to thank the support staff, the TAC team that we've got that really helps. We meet twice a week, and they help guide and give information for the project. And of course, the NRD staff that always helps put all these things together, like cancellation notices out and rescheduling notices and stuff like that. So for anybody that watches later, I'm Becky Ravenkamp. I'm the Bow Creek Watershed Project Coordinator. The Bow Creek Watershed Project is a project with a natural resource district up here in Northeast Nebraska. So I was going to ask anybody that as we go through, you can text questions down in the chat box on your computer. And so just out of curiosity, if you live in the Bow Creek area, do you use the creek for recreational activities? And which activities do you do in Bow Creek in the summer? So you guys can type that in the chat box if you so choose. So you can see that our NRD is pretty big. We go clear from Creighton to Ponca and up north to the river. One of the things that we're tasked with is non-point source pollution, which is how we got the Bow Creek Watershed Project. So if we were in person, I would have had an evaluation for everybody, but the pollutants that we're concerned with in Bow Creek are sediment, phosphorus, nitrogen, and E. coli bacteria. Kind of the background on this project: in 2010, the Department of Environment and Energy did their first testing of Bow Creek for water quality parameters. They found elevated levels of E. coli in the water. So Bow Creek ended up on the integrated report that Nebraska must submit to EPA as an impaired water body in 2012. In 2016, the state returned and did testing again. Also found levels of elevated levels of E. coli, sediment, nitrogen, and phosphorus. So Bow Creek stayed on that impaired water bodies list in the 2018 integrated report. So in 19, Lewis and Clark NRD updated their water quality management plan, included a chapter on Bow Creek, addressing how could we start to reduce some of these pollutants in the stream. They used that information to receive funding for this grant, or for this project. So we're mostly grant funded through the project, through the Environmental Trust and Department of Environment and Energy. And you can see on the screen there, the brown segments are the stream segments that are impaired for E. coli. Just because the other stream segments are not impaired does not mean that they're necessarily have any less E. coli in it. Just means that they don't have a recreational use designation. They only impair streams with recreational use designations for E. coli. So those 4 stream segments cover about 54 miles in Bow Creek. It's important because E. coli can be a human health hazard. It's an indicator of fecal matter in the water, which for me is just kind of the ooh factor. But there was one recorded death in Nebraska because of E. coli in 2020. Usually symptoms are pretty mild: abdominal cramps, diarrhea, fatigue, nausea, maybe fever, but it usually isn't very high. But it can lead to severe complications, kidney failure, and death. And in 1999, a county fair had a E. coli impacted water source. Almost 800 people became sick. 70 of them were hospitalized. 15 of them developed that HUS complication and 2 people died because of drinking that water. So it can be pretty serious. Thankfully, most of us probably don't know anybody that has had serious complications from E. coli. So to simplify this, the EPA says anything under 126 colony forming units per 100 milliliters of water would be considered safe. So in these charts, I have highlighted anything under 126 in green. Sorry, I've got people texting me wanting in the meeting. And then they kind of have a sliding scale, and then anything over 576 would not be considered safe. So anything over 576 I've highlighted in red. Anything in the yellow is kind of that in-between part. And you can see in here, we've got a lot of red. We've got some white. That is 24,000. They maxed out the chart on there. And so, you know, we had some pretty high readings there in 16. So NDEE also did testing throughout the entire year once a month. And you can see, again, bacteria likes to reproduce in warm waters. So when the water temperatures come up, we get some of those red readings. But we have some pretty high readings throughout the entire year as well, which really shows that we've got some concerns. We did some expanded testing in 2021. Here are the results of that, and you can see we definitely have some of those 24,000 colony forming units there in July, and a lot of red. So we've got some concerns. In 2022, we did the same testing. It's looking a little bit better, but it was really dry. And so in week 5, you can see we had a pretty significant rain event in May. And then you can see some of those readings went from 190 to 12,000. You know, 12,000, 14,000, 24,000 in there, which is really an indicator that the E. coli levels are tied to some of the runoff that we get with those rain events. And here I just was curious, so I kind of charted this, and you can kind of see those same shapes in both of those graphs, showing that it's really connected with runoff. So we've got some priority management practices that were shown to help clean up the sediment, reduce E. coli levels coming in the stream, that farmers and ranchers were more likely to adopt or interested in adopting. So we created an incentive and education payment program, which basically will give you an incentive to enter into contracts with other agencies. So whether that's NRCS, EQIP, or CSP, or getting into the CRP contract or whatever. So how that works, if you want to do one of these practices by themselves, the incentive will bring you up to 75% of that estimated cost for that practice. So if you have a practice that is estimated to cost you $20 an acre, and your cost share payment was $10 an acre, our incentive payment would be $5 an acre, bringing you up to a total payment between the two contracts of $15. So that would be your $75 kind of your cost share payment. If you decide to do more than one practice, 2 practices together or 3 practices together in a suite, we will increase our payment to bring you to 90% of that cost share. So on that same $20 an acre practice, our payment goes to $8, so you're getting $18 per acre. And then on the second practice, we will also give you an incentive payment to bring you up to 90%. We also increase the maximum payout to $10,000. If you decide to do a nutrient management plan, buffer strips, grazing management, or livestock exclusion, we'll just go right to 90% because we know that they have the best impact on reducing E. coli. And then for some of the other ones, it's just a per acre payment for like crop rotations or CRP. So if you have a contract through the Bow Creek Watershed Program and your maximum payment is $10,000, we will give you a check for $5,000 at the beginning of the contract and $5,000 at the end, or after you have completed 6 hours of education. So today will count as 3 hours. So make sure anybody that watches this video or gets logged in that we have a record of you being here so you can get credit for that time. You can go to our field day in the summer, that would be 6 hours, or you could go to like a soil health conference or some kind of other training where they're talking about conservation practices, and that would also count. So if you're interested in that, come in and talk to us, stop down at the local NRCS office, talk to them, and I believe they are taking contracts for a new sign up this spring, and so you can go in and talk to them and get the details about that new thing. So because of the winter weather, we've kind of had to shuffle some things. March 15th, we're going to be talking about soil biology's contribution to nutrient management. Virginia Jen and Jim Williams will be talking about that. Virginia is going to really dive into that soil biology, why, what's in the soil, what it does, how we can promote it to benefit the farm and ranch. And then Jim is going to talk about how he's been making compost and extracts and using those on his farm. And then the nutrient use efficiency training that we were supposed to have had this month will be moved to March 30th. And so we'll be talking about nitrogen cycling, some of the new research that they're doing, trying to figure out when that nitrogen is released from the residues. We'll be walking through some nutrient management plans, how to make sure we're taking all of the credit from water and manure and legumes in the rotation. And then Renee and Corey are really going to talk about what does that look like if you enter into a nutrient management contract, what's allowed, what's not allowed, what happens if you think you're a little bit short on nitrogen during this season, how can we adjust that? So we definitely have some good information. We hope everybody can join us for those. Hopefully we can have both of those in person at the NRD March 15th and March 30th. We will send everybody an evaluation after the presentation. If you decide to go ahead and fill that out, we would appreciate it so that we can use that information for more funding opportunities. And then if you want to leave us your name on those, we will use those as for drawings for door prizes. So with that, I'm going to turn this back over to Lance.
Becky, please give yourself a little bit of grace here on the weather thing. If we could all figure out how to control the weather, we wouldn't really have to do all these talks, would we? So yeah, I'm in chilly, not cold, chilly Tulsa, Oklahoma today. So it's raining and stuff here, but certainly better than being home right now, from what I keep hearing. And I'm going to go ahead and jump into different soil health tests. And I say this is Soil Health Test 101. Some of this information I'm going to dive a little deeper than 101, but some of these I'm just going to kind of touch on. Otherwise, we will all be sitting here until midnight if we really want to get into the weeds on all of it. So with that, I'm just going to kind of jump right into this. Becky, I don't know if you're going to field questions, but if you are, feel free to stop me. That's fine. I don't have a problem answering them on the fly. So we'll kind of go through this one, take a little break, and then I've got some other materials. So one of the things I just kind of want to set a little bit of a framework here, and you're fortunate enough, you're going to get to hear from a lot of people in this series. Some really amazing speakers with a lot of different knowledge. But I want to kind of lay a little bit of a groundwork here. When we start talking about soil testing, the first thing to think about is we have to consider soil as an ecosystem. It is not a growing medium. I know that many of you have probably heard this before, but it is important to understand this because it is so difficult to see a lot of the things that we're going to be talking about. It's easy to see trees and it's easy to see grass, but it's very difficult to see the microbes and understand what they're doing. Soil as an ecosystem, though, is responsible for these things plus countless others, but nutrient cycling is a big one. whether it's building organic matter or decomposing additional organic matter, it has a lot to do with nitrogen, phosphorus, carbon availability, and well beyond magnesium, calcium, zinc. So, and that is often done a lot through microbial predation. So it is funny, but these microbes are literally reproducing and killing each other as much as they can. They are fighting, and when your lifespan is 2 to 3 weeks and you replicate, under ideal conditions every 20 minutes. I know Becky mentioned E. coli and the fight and the struggle with E. coli, and it is so difficult because E. coli will replicate every 20 minutes. 1 becomes 2, 2 is 4, 4 is 8. Do the math. Pretty soon you are at a huge number in a very short amount of time. But microbes are also responsible for building soil aggregation. And ironically, they are responsible for destroying a lot of the soil aggregation. And it's funny to say, well, when are they going to do which? And to be honest with you, they're doing it in a continuum, meaning that it's always being built and it's always being torn down. So think of this like a city. You are constantly seeing new construction, and hopefully you're seeing remodeling or rebuilding of previous construction. And then sometimes in order to do that, you have to destroy something first. And so the microbes are constantly remodeling their house, if you will. So I'll pick on a few people here, and I'll pick on myself first. I used to believe that tillage was the #1 destroyer of soil aggregation. I believed that when we pulled a disc behind a tractor, that those disc blades were cutting up the aggregates and destroying them. Physical destruction, like a wrecking ball knocking down a wall. But in reality, the aggregates we're talking about are less than 2 millimeters in diameter. So I don't care how sharp your disc blades are, and I don't care how closely together you put them, your discs and your tillage equipment are not directly breaking down the aggregates. Tillage speeds up the process of aggregate destruction because it oxygenates the soil temporarily, provides carbon, mixes the soil up, and then the bacteria go nuts and they start to tear down the carbon that holds together all the soil. Add a little water, the soil system collapses. So we used to think tillage was that issue. Some of us still do. So no-till. Everyone said go no-till, that'll fix that problem. It'll eliminate that issue of compaction and erosion and all those things. And I can tell you, I have seen 30-year no-till fields that the soil looks like concrete because the organisms are still starving for carbon and resources. They will destroy an aggregate on average every 3 weeks. They also build aggregates. But just like remodeling your house, it takes a lot of resources, energy, and time to do that. But we all know how important soil aggregation is. You are in a watershed. We are all in watersheds. But you here are talking about your watershed, and we want water to leave the watershed after it's gone into the soil and been used and filtered and cleaned, and then to the lakes and streams and rivers, not off the surface, right? Soil structure does that. It also increases the stability of the soil and overall increases the water holding capacity of the soil. I often tell people, I understand, we got to produce food, and then, we talk about nutrient dense food, and we can talk about all those things, but I am a firm believer that we as a species will kill each other over water before we ever kill each other over food. And so water cycles, and if you don't believe that, go somewhere where we don't have a giant aquifer underneath of us and see how well that works. It is becoming a larger problem. So soil structure is incredibly important. The other neat thing taking place in this ecosystem are all of these plant and microbe interactions. There are, we focus on the negative interactions, the disease or the parasites. But a lot of these interactions are mutualistic, or they're different types of symbioses. They benefit the plant and the plant benefits the microbes. So that's called a mutualism, where both are benefited. But there's a lot of other instances with this. And the largest example most of us know about is rhizobium and legumes with soybeans. Some of us also talk a lot about mycorrhizal fungi and the root structure, but there are countless other ones out there. Keep in mind, nutrient uptake is driven by microbes. We think that when we put fertilizer on, or nutrients in any form, whether it's manure, compost, 1034O, that we are feeding the plant. We are delivering it. Well, we're not. The microbes do that job, and the microbes are doing it in a trading system with the plant. Microbes farm plants, and plants farm microbes. We manage the system. So, but very important for disease suppression. Most of our antibiotics come from the soil, and they come from microorganisms. So actinomyces and different organisms like that produce a lot of antibiotics, again, because they're always trying to kill each other. They're farming the plant, and they don't want other issues coming out to be a problem. So those are the types of interactions, and there's countless others. But I'm going to talk about different testing then. How do we evaluate these different parts of the ecosystem? Again, we can't just go count the trees and look at the number of different species or see the deer and the rabbits. So how do we evaluate the health of this system? We are going to have to pull from these different sectors. And I know everyone has seen this, physical, chemical, biological, and then where they overlap, soil health in the center. From a testing perspective, this is what this kind of looks like. So we have things that you're probably familiar with: texture, soil structure in the physical side. On the biological side, organic carbon, microbial biomass, things like that. The chemical side is where most of us are doing soil tests. And that is by and large 10 million soil samples run in this country every year. By and large, most of them are in this realm. Cation exchange capacity, nutrients, balancing, all these different things. The issue when you look at this diagram is that you might be thinking to yourself, so you want me to go pull a sample that is the size of a dump truck and send it into a lab and run all of these tests so I can get an idea of soil health? No, I do not. And trust me, neither do you. If we were to go after every one of these things, we're looking at a soil sample that would be in the realm of a couple $1,000s. And I can't run them all anyway. And I don't know anybody that can. The point is that when we are addressing different issues, we need to understand what the resource concern is. And the resource concern is not the same for everyone. This is one of those cases where you are allowed to say, this is my farm, and I'm going to figure out what works here or what is needed here, because it's not necessarily the same on everybody's operation, right? So we want to address those concerns and then build a testing program around those concerns, because we don't need to just collect more data. I'm sorry for all the university people in the room, but the answer is not always collect more data. We can drown ourselves in information and not really know what to do with it. So I'm going to step through a few of these, and it's funny, I'm talking about soil, and then the very first test I'm going to mention here is not a soil test. It is the cover crop test. The reason I throw this in when I'm talking about soil tests is because in the second part of this presentation after the break, I'm going to talk about how we stack certain things together. And this is a very integral piece. Now, if you're not growing cover crops, shame on you. No, I'm kidding. If you're not growing cover crops, that's okay. This test is still useful in other ways. We call it the cover crop test simply because we had too many people that were growing cover crops, and then they would always ask the question, how much nutrient, how much nitrogen, how much phosphorus is tied up in this cover crop? That's the first question. The second question is, well, when am I going to get it back? When do I get to utilize it for my crop? Okay, well, up until this test, the best way that people would do this is they would do the old field check like I used to do when I worked on the farm. You go down the gravel road at 55 miles an hour, and then you let off the gas, you close your good eye, and you look out the window and you go, yeah, that cover crop looks pretty good. It's 2-3 feet tall, it's kind of thick or whatever, and this is what we put in it. There is 60 pounds of nitrogen in that cover crop. It was literally just kind of that guess. We got to be a little better than that. So how do we sample for this? This is just a general outline. What we're going to do is we're going to determine a sampling size area. The example here is a 3 foot by 3 foot square. If you have cover crops growing and they are 7 feet tall and they are thick like a jungle, you don't need to do a 3 foot by 3 foot square. You can do 1 foot by 1 foot, and you can do that in 3 or 4 locations if you want. And then you kind of like a composite soil sample. It'd be a composite cover crop sample. You shove all that material, above ground material, into a bag, and you ship it off to the lab. Now, what we're going to do with it is we're going to provide you back with this. So we get a wet weight. We get a wet weight on the sample. We dry it to determine moisture. We know the area that you sampled, and we can extrapolate that into tons of dry matter per acre. So it's a biomass measurement. So now you know what the total biomass is of your cover crop above ground. And then we analyze it for all the things you see on the left-hand side: carbon, nitrogen, phosphorus, potassium, calcium, etc. That part of the test works exactly like a plant tissue analysis. So for those of you who are pulling corn leaves or soybean leaves or whatever for analysis, it is exactly the same. We add carbon. So on a regular plant tissue test, you don't get carbon, you get everything else. But we add carbon because we want to know one other thing. We want to know the carbon to nitrogen ratio of that cover crop. And if you've ever grown a cover crop or heard somebody talk about them, you'll hear carbon to nitrogen ratio about 1,000 times. It tells us a little bit about that second question. When will I get it back? The higher the C to N ratio, all other things being equal, you've got 2 cover crops side by side. The higher the C to N ratio, the longer that residue tends to last, because it is just, you're whittling it. Think of the microbe. So think of the guy sitting on the porch with a pocket knife and a stick, and he's doing some whittling. Well, hand that guy a tree trunk that is 4 feet around and ask him to make toothpicks. It's going to take a while. They got a lot of whittle down. That's a lot of carbon to get through. When the microbes are trying to chew this up and break it down, we know that if you go lay a tree in your yard, it'll be there for decades probably. However, if you go dump out sawdust, because now you've reduced it, it'll break down a little faster. And if you do like soybean stubble or alfalfa, it'll break down even faster because it's all different C to N ratios. So from this information, this is a real example, by the way, back to at the end of October of last year. And in this example, we have 5.3 tons of dry matter. This is a pretty good cover crop. 5.3 tons of dry matter, C to N ratio around 28. But notice on the right-hand side, this is where we show you the pounds per acre of nutrient that's tied up in this crop. 4,600 pounds of carbon. Okay, let's put that into perspective a little bit. 1% soil organic matter is 20,000 pounds to the acre. 60% of that is carbon. So about 12,000 pounds in 1% soil organic matter. There's also around 1,000 pounds of nitrogen and 1% soil organic matter. So when we talk about building carbon in the system, and somebody says to me, and I'm not saying that these products don't work, they work for other reasons, but when somebody says to me, I'm going to go put on 2 quarts to the acre of humic acid because I want to build the carbon or I want to feed the microbes, that is like dumping a 5-gallon bucket of water into Lake Michigan. Okay, and you are not changing the carbon content directly with that process. Plants are the most economical way to do so. If you wanted to get 4,600 pounds of carbon buying humic acid products, you will go broke very quickly. Cover crop seed, $30, $40 an acre. Yes, it's an expense, but relative to that, what you're getting back, it's not even close. There's 160 pounds of nitrogen tied up in this cover crop. Now, if this was a pure grass species cover crop, where did that nitrogen come from? Well, it came out of the soil. In this case, this was a mix. There were legumes in this mix. So some of that nitrogen was nitrogen that was scavenged from the soil, and some of it was fixed from the atmosphere through the legumes. How much? Don't know. It's not really that important. What's important is that it's tied up in your cover crop. You got it. You didn't lose it. So that whole nitrate thing that that Becky mentioned in the watershed idea, yeah, that we're stopping that from going down into the watershed or running off across the surface of the watershed. You're capturing it in this biomass. Phosphorus, the other big one, the one that never moves, right? Yeah, the one we were told that never goes anywhere. You got 60 pounds tied up in this crop, 300 pounds of potassium, etc. So that is what we use this cover crop test for. And then in the second part, I'll show you like, how do we get credit for this? How do we stack it? Okay. Here, I guess I have the slide in here where I just highlighted some of those for you to see them. But, this is substantial when it comes to nutrients. I mean, think about, wow, I got 160 pounds of nitrogen there. Well, imagine if you even got credit for 25% of that. You got 40 pounds. Well, what does that equate to in dollars? Does that pay for your cover crop seed? Most likely it does. And especially if you're able to reduce, a pound of nitrogen now is $1 plus. And so, it starts to pay off pretty quickly. I'm going to shift gears real quick, like that transition. So that's what I was going to mention. Now we'll get into the soil test. And the first soil test I want to talk about is phospholipid fatty acids, or PLFA. So I've been running PLFA tests now for around 13 years. I did this as part of my master's work. If you have any really super complex questions about PLFA, I will let you address those to Dr. Virginia Jen when she talks to you in a couple of weeks. No, I'm just kidding. But she does know this very well. So phospholipid fatty acids, PLFA, what they are, everyone's heard of fat, and everyone's probably heard of fatty acids. So we think of fish, they say eat more fish, high in omega-3 fatty acids, right? Eat grass-finished beef, higher in omega fatty acids, right? Those are specific classes. Phospholipids are another class, and all organisms have phospholipids. You and I, your dog, your sheep, and microbes. They are found in the cell membrane. So all organisms are made up of cells, if you think back to high school biology. And in those cells, there are membranes. Now, what's nice about this is that we can quantify these, and then they represent living biomass, because when a cell dies, when the microbial cell dies, it opens up, and these fatty acids are consumed by other organisms very quickly, because they are just high energy fat molecules. We can influence the amount and the type of fatty acids that we see with environment and land management. So there are certain aspects of environment that we can't change, right? It snowed 12 inches today. Yeah, okay. It's cold, right? But there are aspects of the environment we can change. Think about being a microbe. Your environment that you are ever exposed to might be a couple millimeters in diameter. That is your entire world, and that is your entire atmosphere. We can influence that through keeping the soil covered, what we plant, what we apply, um, shading the soil, et cetera, et cetera. We can influence that through land management. So if we look at a bacterial membrane, this is all the fun stuff, and they got all these big words on here because you pull this right out of a biology textbook. This is a cross section, meaning the membrane on the upper side of this picture is the outside of the cell, on the bottom side is the inside of the cell, and you've got all these things kind of going through it, et cetera, et cetera. We're going to strip all that away, and you're left with this. So the little pinkish purple round heads, that's your phosphate molecule, and then the kind of aquamarine teal tail squiggly lines, those are the fat molecules. And they arrange themselves in this way. And the reason is because fat and water don't mix. So when you get into the bathtub, your skin does not just instantly absorb water. You don't gain, 100 pounds of water just absorbed through your skin. It has to pass through this fat layer. So see, this is the argument that fat's okay. That's why I always tell my doctor I need the fat. But this is what keeps the outside out and the inside in. We are going to cause mass genocide with this test. Everyone says to me, well, are you sure the microbes are alive? When you test them, what can I freeze it? Whatever. I said, it doesn't matter because we are going to dissolve all the microbes into a soup, and we are going to pull out all of these fatty acids. We're going to analyze those with gas chromatography. So for any of you that like your crime drama shows, CSI or any of those, you'll always see when they go into the lab, in the background, there is a gas chromatograph sitting on a bench. It is just a standard protocol for all crime drama shows. They have to have it. Apparently they have a big budget because those are not a cheap tool. But we use gas chromatography, and we are able to measure the amount of fat in the soil. And in this case, it's okay. You want to tell everyone that you have a really fat soil, because soil fats are derived biologically. They are not inorganic compounds. They're not clay particles. They're not silt particles. They don't come from rock. They come from organisms. So when we get this is a type of report or table you'll see on the report. And it says higher biomass and diversity are better. Now, diversity is highlighted in yellow because the diversity part is more important than the biomass. Okay. So if we look at this table, we have less than 500, less than 1, 500 to 1,000. So the way we rank these and so on. So the way we rank these is we look at the biomass first. So let's say your biomass is 1,200. Okay, that is slightly below average. Your diversity is 1.45. Okay, that's the right-hand side of that. That's in the good category. So what's your overall rank? Slightly above average, because we skew to the diversity side. Okay. Now, what the problem with the tests like this is that there is no standard ranking established. And you might say, well, then where did you get this table? I created it. I created it after looking at well over 20,000 of these from all over the world and all over the country. And this is what we've come up with. I ran statistics on it and said, okay, this is what we get on average, and so on and so forth. Now, what that means is that as we get more and more data, or as you're working together potentially in your group, within your watershed, and if you're running these types of tests, you can start to develop your own average and your own table and what is good and what's very good, right? Because New Mexico is very different than Northeast Nebraska, and it's very different than Iowa and Illinois, but we had to start somewhere. Now, the biggest thing we use this test for is to look for change. So if it's a report card test, so if you go out and establish where you're at now, you listen to all the other smarter people than me that come in and talk, and you decide that you want to try to implement some different things on your farm. You implement some of those things. You're told that if you stop doing as much tillage, for example, that you'll see more fungi. This is a way for you to verify that over time. So it's not necessarily about where you are, it's about where you're going, for the most part. Like I mentioned, it is dependent on soil type and climate, etc. But again, we can influence that within those regions. We're not going to turn a sand into a silt loam, but we can influence how well that sand functions. There are ratios delivered on this report. The three that are highlighted or bolded here are the three most important ones. The ones below that are really more confined to research type projects. University studies, more tightly controlled greenhouse things, not really that important at the field level. But the first three, the fungi to bacteria ratio, the predator to prey. So I mentioned that there's a lot of microbial predation going on. Predators in the soil are typically protozoans. Their prey are bacteria, and I'll talk about why that's so important. And then we have gram positive and gram negative. And I'm going to step through each of these ratios just a little bit. I think I am anyway. This is the actual report that you see. I have this out of order, sorry. The PLFA analysis report. So on the left-hand side, we have the total biomass, and then we have the functional group diversity index. You can see those are ranked individually, and then we have the fungal to bacterial, protozoa to bacteria, gram positive to gram negative, etc. All of these are individually ranked, and then they are weighted, and you're given an overall score or rank. That is how we are going to track that change. So even though, like right now, it says a protozoa to bacteria are poor, okay? Protozoans come on later. They rely heavily on soil structure. Bacteria don't care too much. We can destroy soil structure or help microbes destroy that structure, and the bacteria don't really care. Fungi and protozoans definitely do. So if we're trying to strive to increase or better our soil structure, that is one of the indicators we might want to watch. And I'm going to step back really quick because I'm going to step back really quickly and talk about these ratios because I don't have those slides in there. So everyone's heard of the fungi to bacteria ratio. Anybody who's ever talked about microbes or soil health, that's right next to carbon maybe now. That is the one everyone talks about. So ideally, they say you want a ratio 1 to 1. With PLFA, you will, I'm not going to say never. I haven't seen it yet, and I've done about 50,000 of these now, a 1 to 1 ratio. The reason is because pound for pound, if I had a pound of bacteria in my hand and a pound of fungi in my other hand, bacteria have about 4 times as much PLFA in their membranes than fungi do. So anytime we run this test, you're going to see bacteria be much higher than fungi just because we're getting more PLFA from them. So when we rank this, a ratio of 1 to 4 or 0.25 is about the same as 1 to 1 using other methods. So I know that's what makes this all really confusing, is that when you read something or hear something, if you don't know the context of how it was measured, much like carbon to nitrogen ratios, right? My goodness, there are You hear people talk about carbon nitrate ratios, and there are thousands and thousands of them. And they say, well, you want your carbon nitrate ratio to be at 40 to 1. 40 to 1 for what? You have to understand what they're referring to. So in this case, when you see this report, if you see a ratio that says 0.3, that means, basically one fungi to every 3 bacteria or so. You'll see a ranking that says good. And you might look at that and go, well, that doesn't make any sense. It's not 1 to 1. It's such a low number. That is why. We used to actually do the conversion and report it the other way, but then I had a lot of really smart people that would call me and say, I took your total bacterial biomass divided by your fungal biomass, and I don't get that same number. You don't know how to do math. So we quit doing the conversion just to save on that confusion. The predator to prey, this is always a really small number. Scale this up to lions and gazelle or wildebeest. We better not have a 1 to 1 ratio. Protozoans can graze on bacteria and they will consume tens of thousands of them every day. And why that is so important is that bacteria are essentially just little bags of fertilizer. Here's another seed-in ratio for you. Bacteria on average have a carbon to nitrogen ratio of around 3 to 1, which means for every 3 carbon atoms they have in their cells, they have 1 nitrogen atom. They are very protein rich. To put that in perspective, soybeans are around 20 to 1, 25 to 1, depending on their growth stage. And corn at maturity is 80 to 1. So we think corn needs a lot of nitrogen. Really, these bacteria take a ton of it. Protozoans on average are 15 to 1. So for all the cattle people in the room or livestock people in the room, what comes out in the manure when you feed livestock really high protein feed? Well, they kick out nitrogen. They take what they need. Hopefully they gain some weight, right? And then the rest of it gets excreted. That process in the soil is called mineralization. And that is nitrogen mineralization. So as the bacteria consume organic material, as they break down your cover crop, as they chew through the manure, as they do those things, the microbes consume and tie up nitrogen temporarily. The predators consume them and release it. And that is the process that takes place. Gram positive, gram negative. A lot of people think this is good versus bad. Gram positive and negative is not good and bad. It has to do with their cell structure. This is an indicator of balance and stress. Gram positive bacteria do better in conditions that you have right now. Cold, blizzard, they do better. Gram negatives don't do as well in drought or severe heat. And so as we influence, as we influence that environment, we are looking to see how balanced that ratio is. And in this case, we expect the ratio somewhere between 1 to 1 and 2 to 1. Gram positives always tend to dominate a little bit. And I'd say not dominate, but slightly overpower gram negatives. But we can track that as an indicator of overall stress in their environment, right? And how well we're mitigating that. So jumping from a biological test to more of a physical measure, keep in mind, though, that aggregates, as I mentioned before, are built through soil biology. They're also destroyed mostly through soil biology. So jumping into this one, it's still a biological test and to some degree, but we're measuring a physical characteristic of the soil. So soil is made up of 3 primary particles: sand, silt, and clay. Now the gravel is on here just to kind of show you a reference in scale. So clay, we can't even see at this scale. Tiny, tiny, tiny particles. And a gravel is 2 millimeters roughly. So how do we build aggregates from this stuff? and what are the results. So we've seen pictures similar to this, I'm sure, in the past. These are different types of soil structure. Kind of the one that we're all hoping for and shooting for is in the top left, and that is granular structure. Often described as chocolate cake, crumbly cottage cheese, and if you don't like chocolate cake, I'm sorry. If you don't like cottage cheese, that's okay. But those are typically the ways that it's described. A lot of us think that aggregated soil structure, and maybe I'm picking on other people, maybe I'm the only one that thought this. I used to think it was more what I would call now blocky structure. I used to think aggregated soil was when you could pick up a dirt clod and hurl it at your brother or sister. That is not soil structure. It is not granular. That is blocky, and those are man-made aggregates. That is the result of compaction and sidewall pressure, et cetera, et cetera. So we think that when we do a lot of tillage, we're destroying that blocky structure, but in reality, we're creating it. And then down below on the left, we have the platy structure. This is where we have those compaction layers. Typically, they're the horizontal ones. Yes, we can have some vertical compaction. There are plates that run up and down, but most of it we see is the horizontal. And then we have massive structure. This is basically where you take single grain structure and add water and pressure, and you get bigger dirt clods. But we end up with this massive structure. And then single grain, of course, is when we do a lot of tillage, especially in dry environments. And then we end up reducing that soil down to its primary particles. Excuse me, I have got something going on. Single grain is going to be, of course, your most susceptible to wind and water erosion. And it also is the one that tends to seal shut. So you add a little water to it and you get the surface crusting. It's because the clay particles float up, the sand and silt settles out in the bottom, and then when the water evaporates, you get this crust across the top. It's really more predominant, that crusting, especially in high clay soil. But we do see it, and so typically then the answer that most people have for that is tickle it a little bit, right? Go out and scrape the surface, break up the crusting. The issue is that as soon as it rains, it's going to recrust. So it's kind of a constant battle. So how do we stop those things? How do we transition those? And this slide is this graph is a little weird because it actually reads right to left instead of left to right, which is kind of odd because I like to think about building the aggregate, not tearing it apart. So we're going to go right to left. So we start off on the right-hand side with primary particles. That's your sand, silts, and clays. You'll notice humus in here, bits and pieces of soil organic matter. And look at the scale of that, 0.003 millimeters. Okay, this is tiny. These primary particles start to get glued together. Plant debris, microbial debris, microbes produce all kinds of sticky stuff. Polysaccharides, which just means mini sugars. Glomalin is the popular one everyone's probably heard of. But they start to glue these together. And as that happens, we build a submicro aggregate. From there, we glue together submicro aggregates into micro aggregates. And eventually they get glued up into a macro aggregate. Now, a macro aggregate, keep in mind here that this is, it says 3 millimeters. That's about the largest of the macro aggregates. But macro aggregates, so when we talk about measuring them, which are the most important? Well, the macro aggregate. Because think of this like you're building a building, okay? You start with primary particles, sand, silts, and clays. You add water to them and you put those into a press and add pressure and you make bricks. Great, now you have submicro aggregates. Well, you start stacking submicro aggregates together, the bricks together, and you hold them together with mortar, which in this case is plant roots and microbial debris, and you start to build a single room. and now you've got a micro aggregate, and then eventually rooms get stacked together, and now you've got a macro aggregate. You've got the final structure. So this is a degree of construction, if you will, or destruction going the other way. And so we can evaluate that. Oops, excuse me. Did not mean to click on that. We can evaluate that by running if I can go back here, by running the aggregate stability test. And the way we do that, and I'll go back to the apparatus and show you, this is a wet sieving apparatus. And so these little black cylinders at the top are sieves. And we take soil and add it to those sieves, and then this apparatus dips these up and down into those tin cans. And those tin cans contain water. Pretty scientific, right? And if you've seen a slate test before, where, you know, I know Ray Archuleta, famous for the slate test, stand a cylinder up with water and drop in which in this case would be more of a massive structure, but drop in a large clod of soil and see what happens, right? Do the aggregates fall apart or do they hold together? And it's the same concept here. So as the water penetrates the aggregates, if they cannot hold together, they literally blow themselves apart and fall apart, and they fall through the sieves and collect in the can. When this is done running, we dry both sets. We dry the can and we dry the sieve, and we look at how much of the original soil weight that we started with is left. How much of it fell into the can, how much of it fell in, or is still in the sieve. And we use different sized sieves to look at the different size classes of aggregates. So on this report, you receive micro and macro. So you get a percentage. You can say, well, we started with 4 grams of soil. Out of that 4 grams, 25% was macro aggregates and 15% was micro. Your total aggregation is 40%. So that is what we are seeing with this type of test. And again, we're looking for a delta, right? A change over time. Then that brings us to water holding capacity, available water holding capacity. So what we have here on the right-hand side is a pressure plate apparatus, and we take soil, wetted, and it gets split into both of these chambers. So one chamber is at, I believe, 1 bar, and the other chamber is at 15 bar pressure. What we are measuring is field capacity. So when it rains, your soils get really wet. And if you wait a couple days, water will move down out of the soil profile because the soil can't hold it. That is called gravimetric water. It runs out of the soil profile. At that point, what your soil has is called field capacity. That is how much water your soil can hold, and it is at capacity. That does not necessarily mean that's how much water you have available, because the other end of the spectrum is the wilting point. And the wilting point of the soil is determined mostly by its texture. So in other words, how tight does the soil hold the water? Now we know that sand doesn't hold water very well. Clay tends to hold soil or hold water very well. So they have different wilting points. And this is what this looks like on a scale. So again, we have field capacity, and the difference between field capacity and wilting point, or the wilting coefficient, is what you have available. This test measures both of those points, field capacity point and wilting point. So when this is reported to you, it is reported as the amount of water you have available. Now, why in the world I don't understand why the developers of this test, the researchers, years ago, report these numbers as grams of water per gram of soil. What in the world does that mean to anybody? How many grams of soil do you have in a soil profile 2 feet deep? So we take that and we report it that way, but then we also convert it into inches of water per inch of soil, and then total inches of water based on the depth that you took the sample. So if you take a 6-inch sample depth and we say you can hold 0.25 inches per inch, it's 1.5 inches in the top 6 inches. And we report all 3 of those numbers on this test. You can run this test to any depth you want. I mean, you can really go down if you want and say, I want to know the water holding capacity, available water holding capacity to 4 feet. You can do that. Now, this is really, again, knowing your context, right? So let's do 2 extremes. People in North Carolina are not overly concerned with knowing what their water holding capacity is. It's not because water isn't important, it's just because it rains a lot more. And they get what they get and they collect what they collect, and they're pretty content with that. Not saying that's right or wrong, but now go out to California and you are operating an almond farm and everyone in California is staring at you because you're pumping water and you are the devil and they're picketing your place. You better know that when you pump water and you pay for it, that you are not putting on more than what your soil can hold. It doesn't make sense to pump 2 inches of water if your soil can hold 1. I really hope that someday in Nebraska, more of us will become a little more conscious about how much water we like to pump. And I'm not picking on any individual, but it's too easy in a lot of cases to just run water. So that's what this test is for. And if you're irrigating, it works. It's very valuable. Again, if you're in a very heavily rain-fed system, not quite as valuable information. Now, what influences this number? Primarily soil texture, which we're not going to change, but secondarily carbon content. So you always hear people say, for every 1% soil organic matter, you can hold an additional 38,000 gallons of water or something like that. Well, this is what you're actually measuring. And so you're building up soil structure, porosity within that texture helps, and then carbon content. Here's a little disclaimer. For anyone interested in this test, it is a 2-week test. The process is 2 weeks. The pressure plates run for 2 weeks, and I say that because we have 3 of these systems now. We just purchased a 4th, and we are still running samples from August last year. That's embarrassing for me to say, but I say it because it's true. We were completely inundated with these last year. We had one research project with 1,800 of them. You can run 40 at a time every 2 weeks. So we spent hundreds of thousands of dollars to buy more of this equipment. But that is the truth of it. We're running them as fast as we can, just full disclaimer. I promise you the rest of these don't take that long. So here's another one. This one's a little bit different, a little new. It's actually incredibly popular, but this is a total nutrient digest. And as its name implies, that's exactly what it is. We are taking a soil sample and digesting it with peroxides and nitric acid to like basically blow all of the organic content off and release all of the nutrients that are in the organic matter and all of the nutrients on the clay particles and everything else to analyze that to determine what the net worth of your soil is from a fertility standpoint. So this truly is all these other tests, these nutrient tests, whether it's a Haney test, which we'll talk about, or a Malic 3 or a Bray 1 or an ammonium acetate, those are trying to evaluate what is available to the plant. We can argue about which one's best, but that's what they're trying to do. In other words, it's looking at the balance of your checking account. This is what you have available to spend today. The total nutrient digest, it's an evaluation of all your assets and all your debts, and it is a net worth analysis. Okay. They might say, now, why in the world would I care if it's not available to the plant? Why do I care? Well, I'm sure you've probably heard or been told that if you're trying to reduce some of your nutrient inputs, the first thing that the fertilizer person will tell you, especially, is, well, by gosh, you don't have it. You don't have anything. So if you don't buy it from me, you're not going to have it and you're going to have some trouble. The second thing you're going to hear is, yeah, but all you're doing is mining the soil. If you're not putting it on, you're just taking it and you're not, you're mining it. Now, there's some truth to that. However, when we get into this other piece, I'll talk about why that's kind of been a little overstated and a little too much influence put on that. So this is what an example of this report looks like. Lots of numbers here. Again, this is a real example. It actually came off the field with the cover crop test. So on the left-hand side, you'll see the list of nutrients that we're analyzing for. Looks a lot like that cover crop plant analysis, because it is. It works the same way. It's the same digest you do for plant tissue. So we have carbon, nitrogen, phosphorus, potassium, et cetera, et cetera. Here are the raw results: 2.54%, 0.221%. Percent and part per million are exactly the same thing, just expressed in a different unit. You just multiply percent by 10,000 and you've got parts per million. But then we convert that into pounds per acre based on depth. So if you tell me you got a 6-inch sample, we equate that out to pounds of nutrient per depth. And then on the right-hand side is something I put together that's just kind of more for fun, because it makes fertilizer people scared. It is your fertilizer equivalent. So I think I've got this zoomed in. So if we look at this soil had 61,000 pounds of carbon. It has 5,300 pounds of nitrogen in it. And this is just the top 8 inches, by the way. So if you wanted to purchase 5,304 pounds of nitrogen, and you were going to buy urea as your reference fertilizer here, you would need 11,530 pounds of urea per acre. Now that should make all the watershed people in the room cringe like crazy, right? Because what would that do? You would need 10,000 pounds of 1152 to get the same amount of phosphorus you have in this soil, in the top 8 inches. So this is here to show you, really show you just what you have as an asset in your account. That doesn't mean it's available. All of it's available. What it means is this is what you got. So when somebody says to you, well, you, according to this soil test, you only have 25 pounds of phosphorus in your soil, you can kindly tell them that they are wrong and show them this test. You have 25 pounds available, but you have 2,300 pounds. So then the question is, well, how do I get access to that, right? Well, all I know is that if I knew I had a safe in my house and I had $1 million cash locked up in that safe, I would try to find a key, wouldn't I? And I would tear my house apart looking for a key. And if that didn't work, I'd try to get out a big hammer. And if that, the process is that this is how valuable this is. How do we get it out? And I'm going to tell you, it's not a product. It's not a magical, system. There's no silver bullet. It is biology. Microbes are the ones that get this out. And if you don't believe that, if you've ever had a chance to travel where there's rock and you go west a little ways out in Becky's neighborhood and you see trees growing out of the sides of mountains, and it's just pure granite rock, and you're going, well, what in the world, how is that tree growing there? And what came first, by the way, the soil or the tree? What came first? Well, you've got a seed that gets wind blown and lands in a little nook, and there's some dust up there, and that seed germinates. How's that seed going to get enough nutrients? Well, it pairs up with mycorrhizal fungi. It pairs up with actinomyces. It pairs up with the endemic microbes that are in the seed. And those microbes start to dissolve rock. They have enzymes to do that. And they feed those nutrients into the crop or into the plant. What does a plant do in return? It feeds the microbes carbon. And if that goes on long enough, you take geology, which is rock and dirt, and you add biology, and now you have soil. And so that is the process taking place. These organisms release this out of these pools into the plants. So really quickly, just before I jump into the Haney test, these are just some general how-tos. And these apply to all of the tests that I've mentioned. Now I say general because everyone's farm's different, and maybe you have slightly different goals, and we will tweak the sampling program around that. But in general, 6 to 8 inch depth. You can use other depths, but you have to include the depth when you send us the samples. It is important. And then you want to be consistent. Don't pull 4-inch samples one year, 8-inch samples the next year if you're going to try to compare PLFA or water holding capacity, because texture, carbon content, oxygen content, all of those things change with depth. We do not recommend doing any of these on a grid sampling program. To be real honest with you, I'm not in the market of selling $7 grid samples, and I certainly can't afford to run $7 tests with these types of analyses. It just doesn't happen. But I also don't want people to go out and spend that much money. We run these on composite samples. We're going back to non-precision ag, if you will. We're going back old school. Look, precision ag, 2-acre grids, whatever. How much variability is in 2 acres? At what point do you just say, okay, we can't pull a sample every 2 feet, right? It's just not economical. It doesn't work. Go back to composite sampling, 10 to 15 cores composited into one sample. Keep these soils relatively cool. If you need to store them longer, you can freeze them. When I say relatively cool, what I mean is please don't throw them on the dash of your pickup truck for the next 2 weeks in July and then send them off. We are measuring biology here. For the most part, we don't want to nuke everything. Let us do that at the lab. Let us kill them all. You could use freezer bags. You can use plastic lined soil bags. We don't care. They can be from any lab, anything, whatever you've got. It doesn't make any difference. We say you can represent up to around 40 acres. Now, you tell somebody 40 acres in North Carolina and they scratch their head because they're saying, well, so I can pull one sample to represent 4 fields. Their fields are small. They're segregated. I understand you tell people that in Nebraska and they're saying, well, I've got a 640-acre section that's all one field. And you're telling me I got to go out and sample every 40 acres on that field. Use a little bit of common sense here. If you've got a nice, relatively flat field, pretty uniform, you're doing all the same management across the entire field, you can go beyond 40 acres. What we don't want to see is we don't want somebody to take their ATV down the pivot road and literally reach off the left-hand side, pull a soil plug, and then send that to the lab and say that represents 640 acres. So that doesn't work either. So around 40 acres, everyone asks me, well, what am I doing year one? Well, year one, you're establishing a baseline. For most of these tests, you're establishing a baseline of where you are now. And for some of you that may have been doing this for 10 years or 12 years, and the tests weren't available 10 years ago, we can't go back in time, but you can still do a baseline, but you can also do a comparison. So if you've got areas of the farm that you haven't done different management on, or your neighbor, I say that kind of quietly, your neighbor, you can pull a soil sample and make a comparison between that and your farm. Now, this is something that guys like Gabe Brown have done for years, right? Because you can't go back in time. The frequency is determined by management intensity. Dwayne Beck in Pierce, South Dakota, always said that management intensity needs to match environmental intensity. In other words, don't try to plant oranges in central Nebraska if you want to make any money. Wrong environment. Same thing with the sampling frequency. If you are going to implement a cover crop into your rotation, but it's once every 3 years, sample once every 3 years for most of these tests. If you're going to go gung ho, you're going to park the tillage equipment, you're going to add 4 crops into your rotation, you're going to go buy 400 head of cows, you're going to just go nuts, probably once every year. No reason to sample more than that, but the testing is supposed to support what you're doing or give you direction on what's working and maybe what's not. Do keep in mind soil temperature and moisture play a huge role here. So don't go out and pull a sample in February through 12 inches of snow and try to compare that to one you pulled in October. Unless, of course, your question is, I want to know what changed between October and February. Because that's really, what effect did the temperature have on this? Because that's really what you're looking at. That doesn't mean that, much like most of us planting corn, that doesn't mean that we plant corn on the date on the calendar, regardless of what the weather's like. That doesn't mean if you pull a sample on May 1st that you're going to have to pull it May 1st every year. Do this within seasons. It's Nebraska, right? It can be snowing on May 1st, or it can be 104 degrees like it was in 2012. And so we just want to keep that in mind, be consistent. So this is the test I'm going to spend a little more time on. We'll dive a little deeper into this one, and it's not because I like it more than any of the others. It's the one that I feel is the most useful, directly impacting management on the farm. And so we'll spend a little more time on this test. The Haney test. Dr. Rick Haney really doesn't like that I call it the Haney test, but I started that 12 years ago, so cat's out of the bag now. Developed by Dr. Rick Haney and colleagues. By the way, Virginia Jen worked with Dr. Haney years ago at ARS and Blacklands Research Station in Temple, so she was a part of this development as well. There were a lot of papers that she co-authored and supported into this that were used as foundational pieces. So before we can really understand the soil, the Haney soil test, I want to talk quickly, just one slide on what the traditional approach to soil testing is. So you pull a sample, you send it to the lab, and we're going to analyze typically what we call quote unquote plant available nutrients. I have NPK there, but NPK, calcium, mag, et cetera, et cetera. And then we also analyze soil pH, and we analyze percent organic matter. And that information gets funneled into building fertility recommendations. Now, sometimes the lab provides those, other times an agronomist takes the lab data and helps provide those. Sometimes the fertility recs are just standard fertility recs with no test, right? But all of that's going back into soil fertility as it relates to plant requirement, crop requirement. Not a whole lot with soil biology there. I've had people argue and say, yeah, but organic matter, is a biological thing. And I say, yeah, it is. But in the context that most of us talk about it with soil testing, it has to do with nitrogen. So they say, well, for every percent organic matter you have, you can take a 30-pound nitrogen credit, right? It always relates back to fertility. And the issue with that is that you cannot take nitrogen out of organic matter and still have organic matter. That is like, think of organic matter as a cake. It contains flour and eggs and butter and sugar. And if you want to take the eggs back out of the cake after you've baked it, you got to deconstruct the cake. Okay. So that is what happens when we take the nutrients out. But we're going to talk about how we can get credit from the organic side of things. When I say organic, I mean organic nutrients, not certified OMRI organic. But how do we get credit from that? So Rick sat back, and I stole this slide from him 10 years ago. he sat back and said, hey, look at that. I even gave him credit at the bottom. I forgot I did that. Good thing I didn't tell everybody I did this. But he sat back. So Rick was interesting because he went to college, did his undergrad, and then he went and worked on farms. So he went out in the world and was working on farms. And after 10 years or 12 years, he said, why are we still trying to figure out the same thing we were trying to figure out 10 years ago when I started? We have the same problems, the same issues, and we're doing the same things all the time. And they said, well, that's because all the information feeding back into those decision-making processes is the same. The traditional soil testing, it's all the same stuff. We've been doing that for 70 years. If everything was great and fine, we wouldn't be having a conversation about nitrogen and phosphorus in our watershed, would we? So nature's way grows a skin for living systems. When that happens in agriculture, we call that weeds, right? But that's all Mother Nature's doing, trying to grow a skin for a living system. Mother Nature cycles nutrients. When's the last time you saw somebody out fertilizing Yellowstone National Forest or the Great Grasslands? That doesn't happen. Diverse, no monoculture. Monocultures do not exist in nature. We spend billions of dollars every year trying to make a monoculture. Now, I'm not telling you to go plant corn and soybeans and wheat and rape and canola. I'm not telling you to do that. I'm just telling you this is why you're fighting those systems. It's because Mother Nature does not like monoculture. Seeks balance. When we get too hot, we sweat. When we get too cold, we shiver. Because our body is trying to reach balance. Homeostasis is that nice, meditation term, right? But Mother Nature tries to do this. When things get out of balance, Mother Nature has a tendency to fix it. Sometimes we don't like the way she fixes it, but it's highly integrated. Millions and millions of years of R&D experience. We have been on this planet a very short amount of time. And whether Mother Nature has all this R&D experience or whether God created it 9,000 years ago, either way, we are not in control of that, and we just try to understand it. One of the neat ones is that plants build root networks. So we think that plants compete with each other, and they do to some degree, but they build networks to support each other. So quick question. Every time I talk about root networks or monoculture, I get this big argument, right, that, well, I can't have anything in my cornfield because it competes with my corn, competes for water and sunlight and nutrients. Let me ask you, what plant competes the most with corn? And I know that I'm not expecting a loud answer here, but it's corn. Corn competes the most with corn. Soybeans compete the most with soybeans. Think about that. They all have corn. The corn plant next to another corn plant has the exact same root structure, has the same canopy structure. It needs exactly the same resources at the exact same time. It competes the most, just like people compete the most with people. And if you have the exact same job and you want to work at the exact same place, you compete the most. And so that is why this idea of competition is always seen as a negative thing. But in this type of context, it is a positive thing most of the time. So how do we test around that? So we're still going to include soil nutrients. We have to. It's part of the soil health process, right? We have to look at NPK, calcium, mag, et cetera, et cetera. We're also going to then include soil organic nitrogen and phosphorus. And again, I don't mean that the term organic in the sense of organic agriculture. I'm talking about nitrogen and phosphorus that's tied to organic molecules, carbon-containing molecules. We're going to look at microbial biomass. We'll talk about water extractable organic carbon. So this is another carbon term. It is a subset of organic matter. And then we want to know the balance between organic carbon and organic nitrogen. So think of this like balancing a ration for livestock. You have energy and you have protein. And the animals perform differently based on what you're feeding them. Too much energy, not enough protein, changes their attitude, health, demeanor, etc. Right? So when we're feeding on corn stalks or wheat stubble, we often supplement with protein. And the other way around if we're just feeding too much protein. So, and it does change, of course, throughout their life cycle of what they need, right? And my goodness, if my phone could ring anymore, I could be an operator. So I'm going to step through each of these a little bit, and we've got soil NPK. I'm going to step through on how we measure this. So I mentioned earlier that different soil tests use different extracts, right? If you've ever had a soil test run anywhere in the country, you'll see different extracts. Malic 3 is a big one. Ammonium acetate, DTPA, Bray1, Olson, etc. Those are different chemistries that are being applied to your soil to essentially pull out whatever nutrient or whatever element they're looking for, okay? Rick Haney sat back and he said, well, wait, why in the world are we using chemistry in a lab that your soil never sees in the field? It was a valid question. So he developed this, he and 3 others. So H3A is a nice little acronym. If you've noticed, most soil extracts are named after the person who came up with it. Malick, Bray, Olson. H3A is Haney, Harmel, and Arnold. That will be on the exam. H3A is a little easier. So this soil extractant is designed to mimic soil solution. It uses organic acids produced by living roots. Now, what those organic acids do is they temporarily change the soil pH and increase nutrient availability. When I say change the soil pH, I'm not talking about the pH that we measure in the lab. That is bulk soil pH. I'm talking on a micro scale. So think of those micro aggregates. It's changing the pH around those aggregates at that scale. These organic acids also serve as a food source. When I say organic acids, this is the primary one that we use, citric acid. Citric acid, of course, is in almost every food product you consume. Malic acid and oxalic acid. And these are just 3 of the organic acids that plants produce. There are several others, but these are the 3 most predominant. And from this extract, we're going to evaluate plant available nutrients. In that list you see there, nitrate, ammonium, phosphate, potassium. Also from this extract, we're going to analyze phosphorus and organic phosphorus. So you'll see up above, we have phosphate, and then we have phosphorus, and then we have organic phosphorus, right? Really confusing, but plants take up phosphate, PO4. So we're analyzing for all the phosphorus in the system that is PO4. The other phosphorus in the system that is not PO4, but it is extractable, it's soluble, it's movable, is the rest of it, the total phosphorus. And when we take total phosphorus minus phosphate, we get organic. The organic is what is left over, and it's not readily available to the plant, but it's available to the microbes. Now, I mentioned PLFA earlier. If you don't know phosphorus is important, PLFA, phospholipid fatty acid, every one of those little sphere groups that were on top of those fats is a phosphate group. So the microbes want phosphorus as well. And so they are going to access it, typically, though, from carbon-containing molecules, because they care about carbon more than anything else, because that's their energy. Plants don't care as much about the carbon. They get it from the atmosphere. But everything else is looking for carbon, okay? That's all I'm going to mention right there on that piece about soil fertility, because honestly, it works the same way. When I showed this list, these are things that most people are used to seeing, you know, on a conventional soil test: copper, sodium, sulfur, magnesium. The difference here is the extract. That's the only difference. Same instrumentation, same calibration, same QA, QC procedures, all of that's the same. The difference is the extract. So jumping into microbial biomass, I mentioned on PLFA, that is one way to measure microbial biomass. Sometimes we don't need that level of detail. We just need to know how many, right? So the way we do that is through soil respiration. And this is the fancy apparatus. Here's my shameless plug, Soil Health Innovations. I build these and sell them to other labs. But running respiration, we used to run Solvita, the gel paddles that you would put in the soil. Those are relatively cheap and economical. If you want to do some playing around on the farm, you can pick those up, I think, for around $10 a paddle. They are a one-time use. So as a lab, when you run 30,000 of these a year, I really don't want to spend $300,000 a year on paddles. So we moved over to this, and we are going to still follow the same process. So inside these jars, we've got little beakers full of soil, 40 grams of soil, dried and ground. And then inside the glass jar, we add water, and the water moves up from the bottom into the soil to re-wet it. And it's basically at modified field capacity. I say modified because the samples have been ground, just like we do for every other test. But this drying and re-wetting process mimics what takes place in your field. And I know I was in Kansas this summer and I said drying and re-wetting, and the guy says, well, I'm still waiting for the re-wetting part, right? And if you go to some areas, I was just in Hawaii last week, I know, rough. And Hilo got 30 inches of rain in 24 hours. And they're waiting for the drying part. But this does happen. And when your soil dries and re-wets, you get this huge flush of activity. Microbes, for the most part, are sitting there doing relatively nothing. Not just because it's cold. They're waiting for conditions to be right. And when you replicate every 20 minutes, you can get a lot done in a week. Right? So when conditions are right, they go crazy, and the rest of the time they do very little. How much CO2 your soil produces is relative to how many microbes you have. So we're incubating these at optimal temperature, we're giving them optimal moisture, and then we are looking to see what happens. And what happens then is this rush of CO2. And the more CO2 it produces, the more microbes are in the soil. And it also is a pretty good indicator of other soil properties, so we'll talk about that a little bit. Whole lot of words here. This is just the information you get from the CO2 number, just the microbial biomass. So you've got this scale on the left-hand side, 0 up to over 200. You've got this kind of ranking scale in here, and then the implications. Notice there is no true average presented in here. Just like when you tell somebody, you know, like, well, the weather's been normal. What the heck is normal, right? There is no average. But again, you're looking at, I mean, on the extremes, you know, on the extremes of high and low, or very low, very high. I mean, look, I don't care where you're at in the world. If your respiration is below 10, it's very low. You're going to have the same issues that other people are going to have anywhere else with the respiration that low. You're going to have the same management concerns when it's very high. It's in between that we work with. But if I just look at a couple of these, so when it's very low, If you look at the implications, very little potential for microbial activity. Makes sense, right? If you don't have very many microbes, how can you expect a whole lot of activity? Slow nutrient cycling, residue decomposition. These are the producers that call me and say, I have corn stalks in my field that have been here for 4 years. And they say, I have a residue problem, so I'm going to bale it all up and haul it off. And you do not have a residue problem, you have a biology problem. And with that, the answer, ironically, is more residue. That scares everybody. More residue. How do I fix my residue problem? More residue, but different residue. Corn on corn on corn, or corn rye is not going to be what fixes that problem. Too much carbon going into the system, but you need more residue. So my analogy here is like building a fire. What you are doing is building a biological fire. And if you've ever built a campfire before, if you start with logs that are 3 feet long and 2 foot in diameter, and you get out a match and you hold the match to it, you don't start a very good fire. And if you keep piling more of that type of fuel onto your fire, you never get anywhere. But you still need different fuel to start that fire. And that's a different kind of combustible, right? So you grab some newspaper, or if you're a silly kid like I was, you grab a can of gasoline, which is never a good idea. I'm not promoting that. But you turn around and you add different fuel and you try to jumpstart that system. Now, as your fire builds and you get more of this constant biological burning and activity and things are really humming, you got to start feeding more carbon, bigger logs into the system. If you don't, the fire burns out. Right? So that is what's happening in this scale across this board. Is we want to see your fire build. Most of us, very few. It's kind of like, okay, that's good. Tone it down a little bit, but there aren't a lot of us in that category. Most of us are in the other side. We're trying to build this fire, get the system running, start the engine, cycle it, and then you can fine tune it. So here's a really funny analogy. I had a friend of mine that said, hey, I got a Corvette from my grandpa. He gave me a Corvette and he's like, you should see this thing. So I come over and look at it and he says, man, look at that tachometer. You see how fast this thing goes? He says, it's like 200 miles an hour. And I said, awesome, let's start it up, let's go. And he says, well, it doesn't run. And I said, well, then it doesn't go 200 miles an hour, it goes 0, or as fast as you can push it, right? You might have a Corvette as a soil system, but you got to get the engine to run before you can polish the tires and, wax the hood and make it look nice. I mean, so it's a joke, but it's true. You got to get the system running here before we can really start to fine tune everything out. And this is the big indicator on this test as to how that works. So stepping in, I'm going to talk about these two kind of tied together because they are tied together. Organic nitrogen and phosphorus are tied to the carbon. That's what makes them organic. So how do we evaluate this? Well, we use a water extract. And this is, I know some of you have maybe heard me speak before, but it is still my favorite thing to say. I had the opportunity to meet Rick, sat on his back patio. We talked about stuff. This was 2010 or 11. I came back. I remember, okay, I'm going to implement this test. I start looking through it and everything. And I called him up and I said, Rick, I'm really confused. I said, water is an extract. I said, it seems way too simple. I spent 9 years at college going through chemistry and biology classes and all this stuff. And he said, well, Lance, he goes, last time I checked, it rained water. And I, of course, me being kind of the smart aleck I am, I said, well, wow, Rick, I said, I'm really glad you went to college. You got a PhD to figure that out. And he says, well, at least I figured it out. He says, you've been going to college for 11 years. You still haven't figured it out. I knew right then that Rick and I were going to be pretty good friends, but it's true. As simple as it sounds, it rains water. Most of your soil moisture in the system is water. It's not anything else. It's got a few things dissolved in it here and there, but it's mostly water. So we use the water extract to try to look at what the organisms can see. We try to see their environment. We want to know what carbon they have available. How much nitrogen is in the system that's soluble? Of that nitrogen, how much of it is in the nitrate form, right? We all know nitrate's soluble in water, right? And how much of it is ammonium? And then we can determine how much of that is organic. What's the ratio between these two? We're evaluating different steps of their system. Because you and I can get up and we can walk to the refrigerator and we can grab something, pull it out, chew on it, eat it. Microbes can't do that. Bacteria and fungi are pretty static. And so they rely on soil water to deliver their food, deliver their nutrients. And so water going down and back up and side to side, and within that system, that's what carries everything in their environment. So a quick message about organic matter versus WEOC. WEOC is just water extractable organic carbon. Organic matter is the quantity of carbon. It's the house the microbes live in. The bigger the organic matter, the bigger the house, okay? Water extractable organic carbon is the quality. It is the pantry. It is the refrigerator in the house, okay? Now, I have seen soils with really, really big houses. 7%, 8%, picking on Minnesota there. But their pantries are empty. And so the microbes over time, much like teenagers, if you don't go grocery shopping and don't put food in the house, they start to tear the house down. Microbes will then start to rip apart soil organic matter as a survival technique. Microbes, just like us and just like livestock, we follow a theory in ecology called the optimal foraging theory. Okay, it's really simple, but what it is presented with two choices for food, an organism will choose the food that provides them either A, the largest amount of energy and nutrition gained for the least amount of energy expenditure, or the one that presents them the least risk of predation by another organism. And you can see this for those of you with livestock. You've got a nice diverse pasture. You turn the cattle into it and they start selectively grazing, and they will come back and selectively graze different things at different times. I've watched cattle walk right past sunflowers and cover crop mixes, and a week later they walk right to them. Because of the different maturity, different energies, they need different things. And if you build a fence like they did on Jurassic Park for T-Rex, and you never move the cattle, they will eventually, unfortunately, start to eat everything. They will strip bark off trees, they will eat thistle, they will eat sumac, they will eat anything they can get their hands on. They'll chew on creosote posts. And you're probably going to go to jail, or you should. But why do they do that? It's because they are starving and now they are forced to eat things that they don't want to eat. Microbes do not want to eat soil organic matter. Why? It doesn't have a lot of nutrition in it, or readily available nutrition compared to plant residue and animal residue. But when they're forced to eat it, they will, and all they're doing is consuming all of their dead buddies and all of the things that were left over from decomposition. Not to sound really grotesque, but think about feeding your livestock what's coming out the back end of the livestock. Okay? That is essentially what this idea is. So I point that out because I've talked to a lot of farmers and I ask a lot of questions, and there are three things that every farmer tends to agree on. Farmer, rancher, doesn't matter what they're growing or where they're at. Number one, the commodity price stinks. Could be better, right? Number two, the weather's never good enough. And number three, I want to build soil organic matter. I've got producers in North Carolina that have 42.0% organic matter on the Carolina coast, in the flats in Edenton. I visited that farm and I asked the grower, I said, young guy, and I said, what's your goal? And he says, build organic matter. I said, okay, here we go. So, I mean, that's why this is so important. And we know that soil organic matter influences so many things in the soil, right? Especially with the water dynamic. And so we don't want the microbes to eat it. So how do we build it and why are they eating it? They're typically eating it for energy and to access this nitrogen. So again, when somebody says, how much nitrogen do I get out of my organic matter? Keep in mind, you're destroying the organic matter too. So the next time your wife or husband or significant other says, I really want you to build a sunroom, but I don't want you to spend any money. You say, oh, sounds good. I'll demolish the kitchen. We'll take all the studs and drywall and we'll go build a sunroom. But now you no longer have a kitchen. Okay. So we focus on nitrogen in two pools. Nitrate is typically what is looked at on conventional soil tests. And it's scary, but if you get east of the Mississippi River, they don't even measure nitrate. Their standard soil test is pH pK. They just assume if you didn't use it last year, it's gone. And as we know, it's not gone, is it? It's just somewhere we don't want it. Tile lines, rivers, streams, lakes, etc., right? Gulf of Mexico. So it's not gone. They just don't measure it. On the Haney test, we're still going to measure nitrate, but we're going to add in ammonium. And then we're going to also add in a fraction of organic matter called water extractable organic N. So what is water extractable organic nitrogen? This is basically a pool of nitrogen that's available to the microbes. It's not available yet to the crop. It comes from soil organic matter, cover crop, plant residue, manures, compost teas, etc., etc. Now it's water soluble. So I get all these people that say, well, it's water soluble, so can't we lose it just like nitrate? Well, we can in theory, but here's why we don't. Microbes want carbon above all other things. So again, presented with two choices. Here's a nitrate ion, here's a protein molecule. In other words, here's a protein pill and here's a steak. Now you choose which one you want. You grab onto that steak. You don't even care where the protein pill goes. So these microbes are grabbing onto these organic molecules. They're holding on to them and they're keeping them tight and they don't go very far. Okay. How do we get it back? Because we're not just here to feed organisms. This has to do with the carbon to nitrogen balance. We need this to be balanced in order to get the nitrogen back out. This is your ration balancing. If we have a carbon to nitrogen ratio in the water extract, okay, again, very different than the seed-in ratio of your cover crop, very different than the seed-in ratio of your cash crop or the manure or the compost. This is what is in the transition phase between residue you see with your naked eye at the surface and soil organic matter. This is in that transition piece. If the ratio of what they're eating is above 20-1, microbes tie up nitrogen. So how many of you, by quick nods of yes or no, actually I can't see everybody, has heard of, well, I would plant cereal rye, but if there's a nitrogen penalty to my cash crop, right? Why is there a nitrogen penalty? And they say, well, it's because the rye scavenges it all up and it, then I have to put more on. And that's not necessarily true. What it really is you've got microbes tying up nitrogen fertilizer to make enzymes and protein to access the high carbon residue of rye. They tie it up. They're better at scavenging it because rye is a really high seed-in ratio crop. Eventually, that nitrogen gets released again. But early on, when your corn is prior to V5, you see a nitrogen penalty. Ideally, we want this ratio between 8-1 and 15-1. Really like it between 10 and 12. So soil organic matter is a ratio of 10-1 or 12-1. It's in that range. If we get below 8, we don't have the energy to do work. The microbes need the carbon for energy, just like you and I do. I can't just take a multivitamin every day and say I'm getting 100% of all my nutrition. Well, maybe, but you're going to die because you don't have any energy. At the same time, you can't just drink Coca-Cola and Pixie Sticks all day long and think that you're going to be okay. All right. Balancing those two things out. So what this looks like, just from this number alone, this is your ratio result. Above 20-1, below 8-1 on the two extremes. Obviously pretty self-explanatory. You know, if it's above 20-1, too much organic carbon or not enough organic nitrogen, right? Implications when it comes to nitrogen. And when I'm using nitrogen here, but this is true of phosphorus, it's true of potassium, it's these other things. Now, potassium doesn't cycle through the microbes quite like nitrogen does. It leaches out of the material. So your corn stalks have potassium in them and it rains and they break down and it leaches out. But there are implications as it results to nutrient management because the microbes break down the corn stalks, which releases the potassium and calcium. So management needs on this side, this is not an extensive list. You know, you can increase legumes in a rotation if you're too high, reduce high carbon inputs, graze longer if you're in a grazing system. That doesn't mean take it all. It just means graze a little longer, you know, give them a couple extra days to kind of, again, not throw huge logs on top of your little fire, jumpstart the system. So you can do a lot of different things within a management context, but I will mention this as well. Don't think that you're going to go ahead and plant corn after soybeans and your C to N ratio in your water extract is going to go from a 12 to a 35. It doesn't happen that way. Same thing, you're not going to plant soybeans one year and have the carbon just disappear and the ratio crash. Where we typically see this becoming an issue is where we've had 15 years of continuous corn or corn wheat. There's a gentleman, picking on him a little bit, but there's a gentleman in North Dakota that has grown soybeans every year for the last 15 years. I asked him why, and he said he always wanted to be a corn bean farmer, and for the first 15 years he was farming, they couldn't grow soybeans there. So he's making up for lost time. His C to N ratio, by the way, of his soil on this test was a 5-1. And his soil was concrete because there's no carbon to hold the particles together. The mortar is gone, and so the particles are stacked. So this is the information we can get from this. And when we get this ideal range, this is where we start to maximize the nitrogen return. And as a grower, that's what we're after. On the front end, we're wanting to tie it up temporarily because we don't want it to disappear into our watershed. And if you really want to not sound environmental about it, you paid for it. So at the very least, you paid for that 30 pounds of nitrogen that just ran into the watershed. So if for no other reason, do it for that, right? But either way, we want to tie it up, keep it out of other people's systems and in this soil system, but we also want to get it back. And so balancing this ratio does that. Ultimately, we provide you with a soil health calculation, okay? The soil health calculation is probably the least useful number on this report. But why it's here is because, much like everything else, everyone said, well, this is really great. Can you summarize this all in one number and tell me if that's good or bad? So that's what Rick did. It's calculated this way. SHC, soil health calculation, equals your respiration divided by 10, plus water extractable organic carbon divided by 50, plus water extractable organic nitrogen divided by 10. And there are a few little deviations from that depending on extreme circumstances, but that's the calculation. We like to see this value above 7, and that is true regardless of where you are, because at 7 or above, we start to see really positive kickbacks out of the soil. We start to see better soil structure. We start to see nitrogen coming out. We really get excited when it's above 10. Now, the next question everyone asks is, well, how high can the number be, or what should it be? Well, in theory, the number can be as high as you can imagine. but the highest number I've ever seen has been right around 50. And it wasn't Gabe. For everyone who thinks Gabe Brown's got the healthiest soil on the planet. He might, but not by this test. His environment's pretty harsh, right? Bismarck. So the highest score I've seen was actually on an organic, it was an organic dairy though, not an organic row crop operation. Organic dairy in Pennsylvania, 9th generation, had the highest soil health scores I've seen. But with that being said, we've worked with some growers in New Mexico that are hovering right around 7, and I can tell you that their soils are phenomenal compared to everything around them, right? So again, you're not going to take a 1974 Ford Pinto and turn it into a Ferrari. It's just not going to happen. So work within your context. The first thing we want to do is achieve the C to N balance. This is what starts the engine. So I don't care how high your respiration is. I don't care how much carbon should I have? Well, the amount of carbon you should have is relative to the amount of organic nitrogen you have, and vice versa. We want those to be balanced because that's what starts the whole process. The cover crop recommendation on the test is provided based on the soil health calculation and the C-to-N ratio. If the C-to-N ratio is out of whack, the recommendation's based on that first. Then it's based on the soil health score, which is most tightly influenced by respiration. So if your respiration's really high, more grasses in your mix, again, more carbon going into the system. And again, if you're in a grazing system where you're not truly planting a cover crop, you're planting a forage crop, then the forage crop is designed around the timing and needs of your grazing operation before it's done for the soil, because the soil will benefit from the combination of those two things. We need a mix that's going to be the right thing for the livestock you want to graze. This is the Haney test report that we provide. There's a whole bunch of numbers here. You're going to see this in just a little bit, so I'm going to zoom right through this actually. And I think that I got a little redundancy on these next couple slides, so I'm not really going to jump into it. I'm just breaking it out to show you how this is presented in different ways. The one thing I will talk about here briefly is if you look down below on the soil health side section, under the water extract, you'll see a number called MAC, percent. Okay, that is percent MAC, or microbially active carbon. The easiest way to explain this is how much carbon your microbes are utilizing. It's a spending rate. So if you think of carbon as how much money you have in your checking account, how much of it did you spend this month? I spent 40%, I spent 80%. Now, what happens if you spend over 100%? You dip into savings, or you bum it from somebody else, right? But you dip into savings. The savings account for carbon in the soil is the organic matter. And if the microbes dip into the savings account too often, soil organic matter goes down, just like our savings account goes down. And eventually you go broke and your world starts to collapse. You know, the bank takes your house and all that fun stuff, right? So the idea here is that we want that percent MAC number to be between 50 and 80%. If it's less than 50%, it tells us that food is not the limiting factor for microbial respiration. And then the question is, well, then what is? Well, if you go pull a sample right now in your blizzard, your respiration is probably going to be pretty darn low, and I'll bet you your carbon number is pretty high. Now, why is your carbon number high? Well, because the microbes haven't been eating a lot since Thanksgiving. And so the reason it's low then is because of temperature constraints. But I've seen it be pH. I've seen soils with pH of 4.8. Microbes don't handle that very well by and large. Soluble salts is another big one. Way too much gypsum, way too much manure too often, and your soluble salts get really high. When you re-wet the soil for respiration, the microbes are living in salt water. They don't do well, they don't respire. So there's a lot of different reasons, but if it's above or below 50%, food is not your limiting factor. If it's above 80%, and that's okay. But if we're seeing 100, and I know you're going to ask, how do you get 120%? Well, we're measuring respiration on a continuum, right? 24 hours, we're measuring respiration. The water extractable organic carbon is a snapshot. But as microbes consume and decompose, other carbon that wasn't soluble 24 hours ago starts to become soluble. It feeds, think of that like a trickle charger, right? And so it's feeding into that pool constantly. So much like your checking account, you can deposit $10 every single day into your account. But if you spend 300 bucks at one time, it takes a while to replenish that, 30 days. So we can get above 100%. And if we stay above 100% for too long, where does that carbon start to come from? Well, a lot of it starts to come out of that soil organic matter, and that's the risk. I'm going to talk about this stuff on this next piece. So much like the general how-tos with the Haney test or with the other test, 6 to 8 inches, it's the same information here. A lot of people think it's different. It's not different. Again, anytime, so down below, anytime. So if you're just concerned with soil health, if that's all you're using this for, you're using other things for fertility management. If you're just using this for soil health, try to wait until your soil temperatures are above 50 degrees, and you want to sample just before you're going to make big management change, and then once every year or every other year again, depending on how intense those changes are. You'll want to be able to track change for 3 years or more. Okay, we're looking for trends. If you're doing the nutrient management side, then your timing of sampling coincides with your application. So if you're fall applying, you're going to want to sample in the fall. If you're spring applying, do it in the spring. We even have people with split applications that are doing this as a pre-side dress nitrate test, essentially, the PSNT. So they're going out and pulling a Haney test, at V8, and then deciding if they're going to put on more, or they're maybe fertigating, etc. Now you can couple that with plant tissue analysis to look at, nutrient deficiencies in the crop. You can also, and that's traditional plant tissue analysis, or you can also do that with sap analysis. So sap analysis is not something that we offer currently at Region Ag Lab. We work with a partner lab, New Age Laboratories in Michigan. So I know some of you have heard of NovaCrop in the Netherlands. Absolutely nothing wrong with that, but they do great work. But you're overnighting samples across the Atlantic to the Netherlands, and it is not cheap. The analysis isn't that bad. It's the shipping costs is what I hear. So New Age Laboratories, Dr. Scott Wall and Jenny Garley operate that side of the business up there. Scott is the CEO of that lab. They do really great work with the SAP analysis, and we work with them. So if somebody were to ask me or want that done, we work with them, get them connected to there. I'm just not the expert in SAP analysis. So if somebody asked me to interpret the results, I'm gonna sit right there and on your side of the table and listen to somebody else, because I do not know how to interpret that one yet. Might be something we choose to do in the future, but if we do, if I have it my way, we will not be reinventing the wheel. We will be working directly with New Age or somebody like that to extend their service, essentially. So that's my contact information if you had any questions on that first piece.